To everybody for this regular branch meeting, and to welcome Mark Edwards, who's going to speak to us about the early years of Jodrell Bank. I'm sure many of us have realised and seen details about Jodrell Bank, but it's nice to have somebody with the full story, because it's so easy that what we receive through the media is a rather simplistic and distorted version. So we look forward to hearing from you. Thank you very much for coming.
Thank you. Thank you for inviting me. Thank you. I call this an early history because Jodrell's coming up to its 80th anniversary, and if I were to cover the whole of the 80 years, I'd need several talks. So I'm hoping I've got enough time to talk about the first 20 years. So we'll see how far we get anyway. Hopefully. It's not moving on.
Try the other one, the other button.
The other button? Oh. All right, okay. So forwards is backwards and backwards is forwards. Right. So no story of Jodrell Bank would be complete without talking about this man, Alfred Charles Bernard Lovell. Now, he was born in 1913 in the outskirts of Bristol, and he studied physics at Bristol University, and he gained his BSc in 1934. Now, I don't know if you've read Sir Bernard's autobiography, but it's called Astronomer by Chance, because after he earned his BSc, did he do astronomy? No. He did a PhD looking at how thin films conducted current, because there was a theory at the time that thin films conducted differently to the bulk metal. So no sign of astronomy at all. And the thing with this story is that there are a number of unlikely events which all came together to end up with the observatory the way we see it today. And that's what I hope to demonstrate is what happened along the way and what could have gone wrong. And in several parallel universes, Jodrell didn't exist because the probabilities went the other way. So when he finished his PhD, they effectively threw him out of Bristol University. They said, oh, you should go and go to another university and widen your horizons, as it were. And he was offered two possibilities. One was to go to London to study under Blackett, and the other one was to go to Manchester and study under Bragg. And he didn't want to go to Manchester at all because Bragg at the time was doing crystallography, and he'd really sewn up the whole field, and Lovell thought, oh, there's nothing new to discover. Whereas this chap, if it moves on, Blackett was working at the university in London, and he was trying to work out where high-energy cosmic rays came from. And Lovell thought, oh, that's far more interesting than boring old crystallography. Well, this is where one of those chance events came about, because Bragg went off to be the director of the National Physical Laboratory, and would you believe, Blackett moved to Manchester. So that really pleased Lovell, which meant he could start doing this new work on trying to work out the origin of cosmic rays. And after a while, he produced this paper where he looked at how cosmic rays went through various layers of lead. Now, the thing to notice is this date, 12th of June 1939. Well, Blackett suggested that he should go to a high-altitude observatory where there's less atmosphere, so that he could see the cosmic rays before they'd been absorbed by the lower layers of the atmosphere. So Lovell got this cloud chamber and other equipment together, was about to hire a van because he was going to travel to France to the Pic du Midi Observatory, which is in the French Pyrenees. Well, looking at that date and going to France, this is not ideal. So the next chance event is that we have the Second World War. And before Lovell could set off to France, things were decided for him because he received this telegram which said, please report to the Bordsey Research Station from Cockcroft. Now, Cockcroft was gathering together the great and the good from all the universities to work on this secret, which was radar. And they've been working on this since about 1935. And this was their headquarters. When the war actually started, they did move to various other locations because obviously the Germans kept bombing and machine gunning them. So he turned up at the research station, and at the time they were working on what were called the chain home radar stations. So you had a set of 240-foot towers. You can't see them, but there's a curtain of aerials strung between them. And then you had receiving dipoles on some other towers. And these were set up all around the, initially, southeast coast, then up the east coast, then down the south coast and up the west, to try and detect German planes flying over. Now, as part of their induction, all these new recruits from the universities were sent off to these chain home stations to look at the radars and see how the operators were looking at the traces and reporting the planes. Well, when Lovell turned up, they operate at their low frequency, so 20 to 50 megs, and about 200 kilowatts. But later on, they did increase the power. And what happened is when he looked at the display for the radar, the oscilloscope, he saw all these transient echoes, and the operators were just ignoring them. And he was saying, oh dear, the Germans are coming. And he was told, oh, it's nothing to do with planes, it's the ionosphere. So Lovell immediately thought, it's these cosmic ray showers. The radar is bouncing off the ionization trails left by these cosmic rays. So he produced this paper, and in this paper, he says it's suggested that the origin of some of the transient ionic clouds generally assumed to be responsible for the low-level sporadic radio reflections may be due to large cosmic ray showers. Now, this paper is very important, not by what it contained, but what it didn't contain, because years later, when he was moving his papers to an archive, he found this letter which was from Eckersley. Now, Eckersley was another physicist, and he'd read Lovell's paper in 1940 and sent a letter pointing out some mistakes he'd made in his calculation. But as Lovell says here, it says, Eckersley suggested we'd omitted a factor in the calculations which might influence our conclusions. It says, I discovered to my dismay that by omission we'd introduced an error of many orders of magnitude which invalidated our proposed research. Evidently, if we'd been able to give attention to it in 41, the incentive for the proposed post-war research would have vanished and Jodrell Bank wouldn't exist today. And what had happened is Eckersley had found this schoolboy error in his maths, and he'd missed out a factor of 8 pi over 3, you know, less than 10. And Lovell thought, oh, okay, it's a mistake, but that doesn't matter very much. But in the last sentence of Eckersley's letter, he said to Lovell, oh, have you considered the damping factor? Because when these cosmic rays go through the atmosphere and they leave behind this trail of free electrons, before they can oscillate in the radar beam, they get absorbed by all the air molecules, and he hadn't taken that into account. And when he took it into account, he was horrified because it was a factor of from about 10,000 to 1,000,000 times weaker, the reflection, than what he'd anticipated. But the crucial thing here is that Blackett hung on to this letter until 1946, when Lovell had been at Jodrell for a year. And had he given it to him in 41, Lovell would have said, oh, it doesn't work. I'm not going to try and observe cosmic rays with radar. So that's yet another chance event. So Lovell's excuse was he was being machine gunned at the time. Now, he went on throughout the war to work on radar installed in aircraft, and he was very lucky because there were a couple of experimental setups on aircraft which were destroyed because the aircraft had crashed, and several of the team working on the radar were killed. And so he was twice, he almost went on those flights. But at the end of the war, he was in charge of this team working on H2S. So I imagine everybody's heard about H2S, which was installed on Lancasters, and that's here. And this worked on microwaves, 3 to 10 gigahertz, using initially a klystron and then later on the cavity magnetron. And it always amused me. It's very ironic because at Jodrell, Sir Bernard banned microwave ovens from the canteen, which used the exact same cavity magnetron. So I thought, well, he's only got himself to blame for that. But of course, they were banned because of the interference they generated. Now, another person, which is very important in the story of Jodrell, is this chap, James Stanley Hay. I'm not sure that he's very well known, certainly not as well known as Lovell. Now, he was a graduate from Manchester, and he joined the Army Operational Research Group during the war. And he worked on gun laying radar. And this is what it looked like. So this is the Mark II anti-aircraft radar. And what he was sent to investigate is the jamming which people saw on these radars. And these were, they found that the stations all around the country were being jammed. But when they were being jammed, we didn't have an invasion by the Germans. So they thought, well, this is very odd. So they sent Hay along to try and investigate this. And what he discovered is that the radars which were pointing at the sun were being jammed, and none of the others were. So what he'd actually discovered is the solar radiation. There just so happened to be a large sunspot group which was generating a lot of radio noise. And later on, he started off by having the radar pointing straight up to see the aircraft. But then when they were sending the buzz bombs over, you know, the first drones, he increased the sensitivity of it by putting on 4 Yagis instead of just the single one, and pointed it horizontally. And later on, when they sent the V2s over, he tilted that set of 4 up. And the other thing that he tried to do besides looking at why there was this so-called jamming, was to try and improve the sensitivity. But he found that no matter how quiet he made the receiver, he could never get rid of the noise. And what had happened is that he'd rediscovered the background radiation from the Milky Way galaxy, which is exactly what Jansky and Grote-Reber discovered back in the 30s. So I argue that this is really the first radio observatory in the country, in Richmond Park. Now, when he was looking at this radiation from the galaxy, he saw that there was one place where the noise shot up, and what was more is that it wasn't steady, it fluctuated. And because he'd been seeing solar flares which fluctuated, he thought, oh, this must come from a star out in the galaxy somewhere. So these objects were called radio stars at the time, and a lot of the work at Jodrell was trying to work out what these stars were and how big they were. So, where am I? Oh yeah. The Gunlane radar was actually in three parts. You had a transmitter, a receiver, and a generator. Now, Lovell, in his calculations, his erroneous calculations, he found that the reflection from these cosmic ray showers would be greater at lower frequencies. Well, as we've seen, he was working on the centimetric radar, which was too short, and what he wanted was low frequency. So we had a word with Hay, and Lovell acquired a set of this radar, and he got the army to trundle it along to the old quadrangle at Manchester University. This is a fairly modern picture. I couldn't find one at the time, but I thought, what happened to health and safety here, taking this high-powered radar and plonking it down in the middle of the university? Mind you, when I was there was a linear accelerator just outside the physics department, and when they powered it up, you had to evacuate the rooms that overlooked it. So I don't think they were hot on health and safety then. But the thing was, at the end of the war, these radars, you could buy a transmitter for £10, a receiver for £5, because they were chucking them down old mine shafts to get rid of them. So if you paid them a nominal fee, you could get millions of pounds worth of equipment. And over time, Jodrell just kept buying more and more of the stuff. So he plonked this thing down in the middle of the quadrangle, powered it up, but, 12th of September 1945 this was on. But these had a better idea. The trams, this is the old university building, and there aren't any trams at the moment. There are trams in Manchester, but they don't go past the university. And of course, they were running on DC as well. So they just generated loads of sparks and interference. So he didn't see any reflections at all. All he saw was interference. So he wrote this letter the following day, 13th of September, 1945, and complaining about this interference to the Manchester Corporation Transport Department. And I think number 4 is interesting. It says, if there's no time which is normally completely free from moving trams, would it be possible for you to cooperate by switching off all tram current for a period of a few minutes at some time during the week chosen by yourself? And I thought, does that mean the trams are running 24 hours a day? Our buses stop at 8 p.m. So I thought that was very odd. They seemed to be going by the university all day and all night. Hopefully I can play this audio and we can hear what what happened next from Lovell himself. We've got a bit of a problem, so I have to do it from here. There's a few seconds delay, so don't get worried.
I asked Rainford, who was then a deputy bursar, if the university had any land away from the university with no electrical interference. So he said, yes, we've got a place, the horticulturists have got a place at High Lee. Why don't you have a look at that? So I went to High Lee. This is in the autumn of 1945. And it was a day of misty rain, and I immediately returned because there were high voltage lines over this particular piece of land in High Lee, and they were already sizzling with electric sparks. So I returned, and the next day or the day after again I said to Rainford, no good, do you have anywhere else? And he said, well, there's a man over there, you see that man smoking a pipe. He is in charge of the University Botanic Grounds at a place called Jodrell Bank. See if you can interest him. His name was Sanson. Now, another remarkable piece of good fortune. Sanson, I hadn't met him before, but I told him that I'd just arrived back with this apparatus, and he was fascinated. He'd seen that and wondered whatever it was. He turned out to be a keen radio man. And I said, look, I understand you have some land about 20 miles south of Jodrell. Is there any chance of having your permission to take this equipment out there where there's no electricity, and seeing if I can be free myself of interference? I reported this to Blackett, and Blackett spoke to the Vice-Chancellor, who was then Sir John Stopford, later Lord Stopford. Fortunately, a very distinguished scientist, a medical man in fact, another piece of good fortune, having a sympathetic Vice-Chancellor. And now Stopford quite reasonably thought and had anxiety that those of us who had been away dealing with massive things for 6 years probably would never be able to return to research and teaching in university. Furthermore, he took the point of view that the main point of those of us coming back would be to help restore teaching and get on with it in university. So with some reluctance, he said to Blackett, why don't we agree that Lovell can take these traders there for a couple of weeks and then find out what he wants to and then come back into the university. So I again summoned Hay, and he arranged for the army to come back and tow my traders out to Jodrell Bank.
This is High Lee. So had it not been a cloudy, misty, rainy day with no line sizzling, it would have been the High Lee observatory, not the Jodrell Bank Observatory. I don't know which field he was talking about, because this is the estate there, and there are some greenhouses, but I believe they belong to the estate, but there's some other buildings up here, so it's possible that could have been the field. But yeah, again, another one of these chance events. Had it been a dry day, it might have gone there instead. Now, Lovell had the presence of mind to actually take pictures on the first day at Jodrell. So this is where the army were towing the generator. And what they did is at the botany department site, there are a couple of botany huts, and there was a trail which led to their compost heap. So they decided, oh, we'll tow the generator and the transmitter away from these botany huts, and we'll plonk the receiver next to the huts. And like all things at Jodrell, it got stuck in the mud. And that seems to be a common theme at Jodrell, that whenever they move anything, it gets stuck in the mud. So this is a picture of the generator stuck in the mud by the compost heap somewhere, and the transmitters a bit further up onto the field. And this is the famous picture that everybody sees, which is of the receiving hut, but the transmitter is over here by the tree. And you can see there's someone up there just in the aerial, which is just a Yagi pointing at an angle, because obviously it was meant to detect low-flying aircraft. So it gets to Jodrell, powers up the generator, which didn't work because there was ice in the fuel lead, so we had to get the local farmer to sort that out. Got the generator running, switched it on, saw loads of echoes. I thought, great, it's working, no interference, but far too many echoes than he'd have thought were coming from cosmic rays. Now, the crucial thing is this was the 12th of December, and if you look at this article from the Aspect of the Heavens for November and December 1945, it says the Geminids reached their maximum on December the 12th. So the Geminids are a meteor shooting star shower. And so what he was seeing, he wasn't seeing echoes from cosmic ray trails, which we all know he couldn't see anyway, but he hadn't seen the letter at this time. He was seeing reflections from meteors instead. So when he saw these, he thought, I've got to work out which reflections come from meteors and which ones come from cosmic rays. So he asked these are the botany huts still exist, and they've been restored, and that's what they were like in 2002. And the following year, they moved into the field. They moved the receiver into the field. Right, okay. So what he did is he found that amateur astronomers knew all about meteors, and the real expert was Manning Prentice. And so he was the director of the meteor section of the BAA, and they dragged him along, plonked him down in a deck chair outside their receiving hut, and he looked at the sky with his naked eye and a piece of string. So every time he saw a meteor, held up the piece of string and read off the stars along it. And he would yell, and those in the hut looking at the oscilloscope would see if they could see an echo. And they found that if they had a visible meteor, they'd see the echo, but they saw many more echoes and couldn't see any meteors at all. Because obviously you need a lot of ionization, a lot of light coming from it for you to be able to see it with a naked eye. And they observed the the Perseid meteor shower, which was in August, and then they wrote this paper about what they'd seen. And they said that good correlation with meteors was obtained for echoes lasting more than half a second. The correlation with echoes of shorter duration was very poor. Now, what was suggested is that they should look at some of the other meteor showers, but the aerial on the radar they were using, it was pointing at a certain angle, and they couldn't change that. They wanted an aerial which they could look at any part of the sky. And so what they did is they got hold of this searchlight radar and mounted on it about 5 Yagis to make it sensitive. And this thing you can point at any part in the sky. And it was built by John Clegg, who came along to join Lovell, and he was an antenna expert. And they, Prentice suggested they looked at what was called the Geocorbinid shower, meteor shower, because the Earth was going near the head of the parent comet, and they expected a lot of meteors. And boy, did they get lots of meteors, because they had 168 per minute of these things. And so what they did is, before they got to the maximum of the shower, you could read them off individually off the screen. But at the maximum, they made a cinefilm of it and then looked at the individual frames afterwards. And this is part of that cinefilm. So each line is a little piece of cine. And it's a bit difficult to see, but there are some echoes that you can see at particular ranges that came from that radar. Now, Hay as well was observing this, and perhaps these are a bit easier to see. And you can see that there's an echo at a height of 105 kilometres, and you can see how long it lasts, for about 10 seconds as it flies across the sky. And he took many of these pictures, all more or less around the same altitude, about 100 kilometres. Now, the searchlight came on a little trailer, but they took it off that and mounted it in this concrete base in the field. And they also acquired what was called a Park Royal, which was an army truck made by the Park Royal Company that also made London buses. And of course that got stuck in the mud. So this is the place where it got stuck in the mud. But the interesting thing is there's actually a cinefilm of this, and hopefully it's going to show. Well, it did up there. We had Halloween yesterday, so it's rather spooky, this. But you can see how it's relatively easy to rotate. These are the aerials and the searchlights in the middle. Someone else here pushing it. Now, unbeknownst to me, when I went to Jodrell 50 years ago now, exactly 50 years, I used this searchlight mount, but in those days, that was all that remained of it. And back in 2 or 3 years ago, it's even worse. It's only the base that remains. And would you believe it? This is a grade 2 listed building. And what we used it for back in the 70s is we would put an aerial on the top, rotate it, and then have another aerial in the field, put a signal generator in it, and just record the polar diagram. So we'd record the signal strength from the aerial on the rotating platform. And so you could see when the arrow was pointing at the transmitter, it would be high, and when it was at right angles, it would be low. But yeah, it's strange it's a grade 2 listed building. I think they're going to do some restoration, but I can't see how they can restore it. Very strange. Now, if you go to Google Earth, you'll find in their historical slider, there's actually a picture of Jodrell. Now, they claim that it's from 1945, but as I'll show you in a minute, it's not from 1945 at all. And what we can see here is this is the gun lane radar, That was the first radar that came along. That's the searchlight. That's the Park Royal truck. And the interesting thing is this circular object. And that's how I know it's not 1945, because that circular object is the transit telescope, and that wasn't built till 1947. And incidentally, the botany huts are down the bottom, and this track is the track that led to the compost heap, which is around here. Now, what happened here is that in 1946, the year before, that's when Lovell was given the letter from Eckersley that said, oh, your calculations are a load of rubbish. And so Lovell decided he needed a much bigger telescope to be able to see these echoes. And initially they tried building a huge broadside array out of dipoles, but it got so dangerous they decided, oh, that was a bit dodgy. And then Clegg suggested that they build this reflector. And this is a ground view of the site. And the locals called it the fairground because of all these strange structures. So we've got the gun lane radar here. There's the searchlight behind, the Park Royal, and then there's this very tall mast, and you can just about see these vertical poles. And they were the supports of a huge reflector. This is where they were, they constructed it themselves. This is Lady Lovell, Joyce Lovell, John Clegg, and I think this is Brian Lovell playing about in one of the trenches. And what they did is they put these poles up and then supported a wire parabolic dish. So the idea was the radio waves would come down from the sky, reflect off the dish and go up to the focus. Now, they finished this in 1947, and then they got a student, Victor Hughes, who started work on it in November of that year. And it operated on a frequency of 72 megahertz because that's what the radars used. But he wasn't doing radar, he was looking at this cosmic noise that came from the Milky Way. And the idea being that, okay, it only points upwards, this aerial, but as the Earth rotates, then it looks to strip of the sky. And in this part of the world, the Milky Way does go across the zenith once a day. So he started working on this, but things really took off a couple of years later when Robert Hanbury-Brown joined. Now, Hanbury-Brown was another pioneer of radar, and he was one of the ones who was at Bawdsley Manor in the 30s, 1935. Now, bear with me because I've got a recording of him. Which I hope.
Yes, I joined him in August 1949, and the problem was to apply this existing 220-foot reflector to radio astronomy. And this involved really doing the whole thing. In other words, putting in a decent feeder system. I bought a coaxial cable from the BBC, putting in a decent stabilized receiver, where we copied the technique partly of Ryle and von Berg, developed at Cambridge, and we built our own stabilized power packs and so on, and the whole thing was to make the receiver sensitive and stable. And I did this, and we started surveying the sky with this instrument, and we went on for several years doing it.
Well, surveying the sky is easy to say, but you had to pick out something to specialize in.
It's an extremely difficult operation, because in point of fact this instrument was not designed to have a steerable beam. The mast, 125-foot mast in the middle, had 18 guy ropes, and in order to change the direction of the beam, you had in fact to manipulate 18 guy ropes and tilt the steel mast over.
Right, so you did not do it...
two theodolites and two people. But one of the first experiments I did was to map the radiation from the galaxy and radio stars in the galactic plane and that sort of thing, and then decided that I would like to see whether or not the Andromeda Nebula, which was the nearest galaxy similar to our own, also radiated radio emission, whether radio emission was in fact a peculiarity of our galaxy or whether it occurred in other galaxies.
Right.
And that was the origin of that paper.
I see.
So what we did was we took the model of the Andromeda Nebula and said, if this behaves in the same way as the Earth, I mean, there's our own galaxy, not the Earth. If it behaves in the same way as our own galaxy, then we should get a certain signal from it. And that was the origin of that experiment. And it was the first extragalactic source, really, that was done.
Right. But now...
Yeah, so as he said, what you had to do is to adjust all these guy ropes to try and tilt the mast over to point the telescope at a slightly different part of the sky so it could get another strip of sky. And what I read is it used to take them about 3 or 4 hours to do that. So it wasn't a very quick experiment at all. And the telescope was the largest telescope in the world, 218 feet across. Now, originally it was on 72 megs, but they virtually doubled the frequency to try and get a narrower beam. So it was a 2-degree beam. And so what you did is you tilted the mast by 2-degree steps. And so then you could plot out what you could see in the sky. And this is Hanbury Brown and Cyril Hazard looking at one of the strip charts that came out of the receiver. And this is what they saw. So when this radio star, which was the one that Hay saw in Richmond Park, went through the beam, you had this enormous great spike. And it's in the constellation of Cygnus, which goes directly overhead us. And because it was the first one they saw, they called it Cygnus A. And this is what he was talking about. This is the response when they're looking at the Andromeda Galaxy. The Andromeda Galaxy is, what, 2.2 million light years away. So it's radiates the same as our galaxy, but because of its vast distance, you only get a little response, but at least you can see it. And that was the first time people had seen that other galaxies radiate the same as our own. And this is the contour plot he produced. So the optical bit is their elliptical, and these are the radio contours around it. So they weren't satisfied with having to adjust 18 guy ropes to look at a different part of sky. So they designed this tiltable mast, this latticework mast, which only had a single winch wire to change its position. So that was the drawing, and surprisingly, the actual thing looks just the same. So you can see this is the winch pulley, and there's a counterbalance weight on the other side. And the wire mesh, which was just a loop of wire going round and round, has been replaced with these sort of hexagonal panels. We've got a colour picture from 1958, which shows the mast tilted down, and they had this platform where they could change the aerials and then tilt it back up again. So it was a lot easier to use than the original. So in 1949, this is what Jodrell looked like. So we've got a powerhouse which had a diesel generator in it, the searchlight aerial, the Park Royal truck has now been replaced by a building, still called Park Royal to this day. That's the transit telescope. Incidentally, the size of the telescope was determined by the distance between the Park Royal and the fence. This is the moon hut, because they did radar bouncing off the moon from there. That's radiant hut, because they used that to find where meteors appeared to come from in the sky. Cosmic noise hurt because they looked to the Milky Way from there. Polarization hurt because they tried to measure the polarization of the radiation. A workshop, electric and mechanical workshop, and the main office. All these buildings still exist, and a lot of them are also Grade 2 listed. So that's what it looked like in 49, and this was the inside of one of the huts in the 50s, and you can see the radar display. And this is, the echoes are getting far more sophisticated now. And from the little wiggles, you can work out the speed of the meteors. I used these huts 50 years ago, and the inside still looked the same. The radar wasn't there, but the rest of it looked exactly the same. Now, in the following year, 1951, Sir Bernard was made the first professor of radio astronomy. And these days, they all line up in front of the Lovell telescope. In those days, they lined up in front of the searchlight aerial. Now, out of this group, only Sir Bernard and John Davis, or we always called JG, were there in my time. All the others weren't. And he's standing on his right side, and that was always his right-hand man. Sir Bernard would always ask JG to do things, and he was always, you know, looked upon as the senior researcher there. Now, the interesting thing about this picture, you'll notice, is there's a woman. And Mary Almond, we can, oh, if I don't walk into the thing, we can hear from her, hopefully. She's very quiet.
And he decided to move out there. So, at the end of our first year, he asked the class if any of the boys would be interested in spending some time sort of digging trenches and mixing concrete and the other tasks that they needed at Jodrell. After the lecture, I went to see him and said, would there be anything for girls to do at Jodrell? And he said, yes, he was sure he could find us something. So my friend and I spent 2 weeks working at Jodrell Bank, living in Miss Verity's caravan, as I said, and we sandpapered rust off an old army searchlight that they were going to attach an aerial to. That was the searchlight aerial we saw before. This was a summer school that they had. Lovell was lecturing in the physics department, and he got students to come along to help. And although she started off by brushing off rust, she actually went on to do important work on the velocity of meteors, working out their orbits. But the other interesting thing she did after that was, besides getting married to Jim Pickering, who was Blackett's technician, she helped out at Blackett's hut. Now, this hut was constructed using copper nails. So these are copper nails. Because what he did, he put a very sensitive magnetometer in it. Because at the time, they were trying to work out where the Earth's magnetic field came from. And there was this theory that if you rotated a lump of metal, it would spontaneously generate a magnetic field. So they tried to measure the magnetic field from a 10-centimetre lump of gold, which they borrowed from the Bank of England. And this thing was worth £1 million in today's prices. And they took it to Jodrell on Jim's bike. And they did this experiment trying to measure this magnetic field, and they saw nothing because the theory was wrong. But the important thing is they then went on to measure the direction of the magnetic field in rocks. And Mary discovered that the UK hadn't always been in the same place. It had drifted because they saw that the magnetic field of these rocks didn't match the current magnetic field. So although she started off with brushing rust off, she did do some important work in the end. Now, another couple of interesting characters were Jennison here and Dasgupta. Dasgupta was the first Indian radio astronomer, and together they worked on what was called the intensity interferometer. Now, this is them in the lab looking at one of the charts. And the interesting thing is this oscilloscope over here, I discovered recently that it still exists. Someone had got this from a junk shop, and on the top of it, there's a sort of slug shape, and it says Jennison. So that oscilloscope over here still exists. But they were trying to find what the size of these so-called radio stars were. And what they wanted to do was to have two receivers placed at a vast distance away from each other to see if they could form what was called a microsun interferometer. And the thing is that if you've got separated aerials, it acts like a huge dish. And so the resolving power, the size of objects you can see, is smaller the further apart these two dishes are. But the problem is, if you want to make that sort of interferometer, the two receivers have to be locked exactly together. And at that time, they had no way of doing it. But Hanbury-Brown had this insight that if you looked at the way the amplitude varied, the intensity of these signals, they were correlated. So if you can imagine, you've got an old AM radio here, and you've got one in the middle of Birmingham. You tune to the same station, you'll hear the same music, so that's correlated. But they're not on exactly the same frequency. So they did a few calculations and decided, oh, this will work. So they tried it out on the sun. So this is the array at Jodrell. So you've got one receiver here, one aerial here, and the other one there. And they saw that it worked on the sun. So what they did then is to put one of the aerials on the back of a lorry and trundle it off into the middle of the country. And the first place they plonked it down was outside Lovell's house. But what they then did is they took it around to unsuspecting farmers' fields and plonked it down there. And they recorded the amplitude of the signal and then sent it back with a radio link back to Jodrell, and there they correlated it with the one from that was in Jodrell's field. I'll skip over this audio because I'll run out of time. But when they were looking at the two brightest so-called radio stars, they found that one of them in the constellation of Cassiopeia made sense because it looked like it was from a circular object, but the other one in Cygnus didn't make sense at all. And the intensity interferometer is very insensitive, so this thing is quite a large array, 36 by 12 meters. So this is their observation of Cassiopeia A. This is the one that made sense. So you've got the output from one telescope as it goes through the beam, the output from the other, and the bottom is the correlation. So it shows that the theory works. And this is where it looks like a present-day radio image. It's supernova remnant, so a star's been in the middle, exploded, and all this gas is radiating radio waves. So that made sense. But when they looked at Cygnus A, they used different baselines. So they put their aerials east-west, then north-south, then northwest, southeast, to try and get an idea of what the source looked like in 2 dimensions. And they came up with this correlation curve, which is characteristic of a double source, and this is the model they had, two rectangular blobs in the sky, and they couldn't work out why on earth are there two blobs. And when they went on to look at other so-called radio stars, they found quite a lot of them were two blobs. And if you look at a modern day radio picture, this isn't optical, this is radio. You see why there are two blobs, because this is a supermassive black hole in the middle of the galaxy, and it shoots out two jets. And when they strike the intergalactic medium, they start to radiate. So these are your two blobs. And in fact, there are some sources where you can see three blobs. You can see a blob from the black hole in the middle as well. But this was the first time people had seen this. So they were the pioneers. Now, I remember years ago, there was a cartoon I saw, I think it was in New Scientist, where they had an optical bench set up with a laser beam going across it. And the caption on the cartoon was, well, we can do it with string, now let's try it with light. And Hanbury Brown had the same idea with this. He thought, we can have an intensity interferometer with radio. We'll try it with light. Physics is the same. You know, they're both electromagnetic waves. What's the problem? And the quantum physicist said, well, it'll never work. Either one telescope or the other's got the photon, then they can't have two arriving at the same time and be correlated. It won't work. Well, the fact was it did work. And it became known as the Hanbury-Brown Twiss effect, and they had to rewrite the quantum mechanics books after that. But he acquired, he acquired two more searchlights, and this time he actually used the mirror and put a photomultiplier in each one, and spent many an hour in the night in a cloudy, rainy Cheshire, measuring the diameter of Sirius. And he later on decided that Cheshire was no good for looking at doing optical astronomy. So he went off to Australia and built huge dishes on a track to measure the size of other stars. Now, in 1954, a couple of years later, they'd worked out how they could lock the two receivers to the same frequency. And that meant they could use a far smaller portable array. And this shows one set up in the country. And the radio links, one radio link brought the signal from Jodrell to lock the oscillator, and the other link sent the radio astronomy noise back. And it worked on 150 hertz, smaller collecting area, and they used 200 meg radio links, which were unlicensed. We'll see in a moment what happened with that. The interesting thing to me is that the two students who did this work, and they looked at something like, I don't know, 200 or 300 so-called radio stars. Anthony Thompson and Henry Palmer. Henry Palmer was actually my supervisor in the 70s. And they brought the signals back to Jodrell and then correlated them in this receiver rack. And you can see the power supplies all use valves, the receivers all use valves. And this, to me, looks like a bit of Meccano. It's probably a mag slip it's driving. Because what they did is, as the source goes through the beam of the telescope, you get these very rapid fringes, and they use this rotating mechanism to slow the fringes down. But yeah, it's a bit of Meccano. And they, at 56, they reached the cat and fiddle, and this is where the 200 megahertz comes in. Their unlicensed link, because that was close to the frequency used by ITV, and that really upset the landlady of the Cat and Fiddle. she couldn't, well, I don't know if Coronation Street was on then. It's been on for donkey's ages, but wherever the soap was at the time. And the reason they went to the Cat and Fiddle is you've got this wonderful view back to Jodrell, so their radio link was a direct link. Now, I'll have to speed up, I think. The important other telescope in Jodrell, although it didn't look very important, was this 30-foot dish, which they used to make it easier to try and look at this cosmic noise coming from the Milky Way. And what happened in 1950 was that Lovell said, oh, wouldn't it be nice to take the transit telescope, which we can't move, and plonk it on the same mount as this 30-foot dish here. So they produced a design for a large telescope, which was going to be 250 feet across, mounted on 2 towers on a railway track, and they wrote all this down in what was called the Blue Book, where they gave justification for the objects they could see with this fully steerable telescope. And they were going to plonk it down here in a field, a couple of fields away from the existing transit telescope. But what happened is they really wanted this site, this field, but it was owned by a woman who, fortunately for them, shortly died. Then Lovell had an argument with his 5 sons and managed to, in the end, buy that field. So the telescope was actually built in the field next to the railway line. And this was the design for it. So when they were doing these observations from the transit telescope, although they were in the middle of Cheshire, they still had interference from the local road. So what they did is they designed a dish where the focus would be in line with the edges of the dish. So that dotted line shows you where the bowl is. There are 2 bearings, one here and one there. And then there's a central bearing, and then the towers are on railway tracks. And there are 4 non-driven bogies and a couple of driven bogies on each tower. Now, the other crucial thing is this, what's called the stabilising girder in the middle. Come to that in a minute. This shows you a closer view of the dish. So you've got the aerial is in line with the edge to try and cut down the interference. That made it very difficult to feed, because it's difficult to design an aerial which is sensitive all the way round in a hemisphere. Later on, with the newer telescope, that aerial was moved out. Now, they started pile driving. Now, I always look at this and think, it's going to take them ages to try and drive piles down using this. Piles down through the Cheshire mud to the rock beneath. They started on the 3rd of September in 1952. And you can see the construction here. They built the 2 towers first, and then built up a tower scaffolding in the middle, and then put the supports for the dish on top of that. And to do the drive, the elevation drive, they took some scrap circular racks, I don't know what you call them, gear racks, from 2 ships, HMS Revenge and HMS Royal Sovereign. And the drive for the large guns was this circular track with gear teeth on it, and they bought these and plonked them down around here so they could drive the telescope in elevation. And this shows you putting in the ribs to support the dish. And then that's the central tower
that they're constructing. You can see the metal panels. Now, the original design was for a wire mesh, but they, when they were doing the design, it was for meter wavelengths, so you didn't need a very fine mesh. But in the early 50s, they discovered the 21 centimetre line, which is very important. And so they said, oh, we need a much finer mesh, but they're worried about the wind loading, differential wind loading, when ice formed. And the other thing is that the government said, oh, we want to use this dish for radar, for looking at rockets coming across. So they wanted it to work at a higher frequency as well. So in the end, they used metal plates instead of a wire mesh. And so you can see a chap here welding them together. And I was always told they showed how strength their welding was by jumping up and down on the plate after they'd welded it in position. So this is it, nearly constructed. And you can see where there's the railway tracks, the non-driven bogies at each corner and the two driven bogies at the bottom of the tower. And it was constructed by the United Steel Structural Company of Sheffield. And these are their employees proudly standing in the dish. These to me look like the office workers rather than the people who constructed the thing. Now, to come back to that damping girder, when they were designing the telescope, they designed it to stand winds of 80 miles an hour. And then someone said, oh, have you heard about the Tacoma Narrows Bridge, which oscillated in low wind speeds and then collapsed? And surprisingly, they hadn't heard about this. So they put a model of the telescope in a wind tunnel, and sure enough, at low speeds, it vibrated and fell down. So they thought, that's not very good. So they put this stabilizing girder on. This is non-load bearing. It's just there to stop these oscillations. And if you look closely at it, it uses truck tires to support it. Well, I suppose they're nice and springy and available. So, yeah, someone earlier showed me the one of the horizontal trunnions, and this is the later one, which has got the cable rotator on it. So this thing with the rivets in it is a cone, the cone that joins up to all the girders that form the dish. And of course, you've got to get cables down from the tower across a rotating structure. And you've got a second rotating structure at the bottom of the middle. And then this is Lovell at the control room. And you can see all the fancy dials. The whole thing was controlled by an analog computer. And this is one of the displays, and you can see these wheels here, they drive the displays, and they're all part of this analog computer, because you have to translate right ascension and declination into altitude and azimuth. As objects go across the sky, they don't go nicely just straight up and straight down, they go in an arc, so you've got to have some means of working out where the object is, and they use this analog computer. So this is the completed telescope, looking across the original transit telescope here, and you can see the telescope in the background. And Charles' husband was the consulting engineer. Nobody wanted to do the job at all, but he said, oh, it can't be too difficult. He said, oh, it's just like putting a swing bridge across the Thames. It was finished in July 57. They used it on the 2nd of August to look at the Milky Way. But the main problem with it,
HS2, the original estimate was £259,000. Well, in fact, the original estimate was 154,000, but that was later changed to 259. What intrigues me about this is from the Blue Book, is that the somewhere on it, oh yeah, the consultants' fees went from 3,300 in 1950 to 9,600. So he tripled his salary. So the original estimate was for that, but the final cost was 750,000. And the problem is Lovell had spent all this money and he hadn't got the funding, and he was in danger of being jailed in debtor's prison for falsely spending all this money. The Air Ministry, when they said, oh, they needed the telescope to operate at a high frequency to do this radar on rockets, they said, oh, we'll give you some money for it, and they never did, because the Treasury said, oh, well, we're funding it through the university grant, why we can't fund you twice, so they never gave the money. So he was in dire straits, and he said what he needed was a miracle, and what he got was another fluky miracle, which is the launching of Sputnik 1 on the 4th of October. And this is a view of Sputnik 1. So you had some batteries, a transmitter. What intrigues me is there's a cooling fan, so they must have enclosed some air in it, because fans don't work in space. And a few aerials, and this thing they launched, and of course it transmitted on shortwave, so anybody with a shortwave radio could hear the bleeps from it. So it was on 20 and 40 megahertz. And after it was launched, he had this call from the ministry saying, are you tracking it? And he said, oh, waste of time, anyone with a radio can hear it. But what they were interested in was the launch rocket, because they said the next one, it could have an atom bomb on it instead, because it was an intercontinental ballistic missile. So they quickly mounted a radar onto the telescope, and this is a famous photograph where he shows the echo from the rocket as it whizzes across the Lake District. And he said that instantly they went from being wasters of money to being, you know, the most important people in the country according to the media, because they were the only ones in the world that could track these Soviet missiles. Now, when the Americans saw the launching of Sputnik, this is where the space race started. And Lovell one day in 1958 had this phone call that said, oh, there was this top secret mission, and the American Army want to launch their own ballistic missile and see if they can hit the moon with it. And they told him, don't tell anyone at all, it's top secret. And the next he knew was this lorry turned up. Here it is stuck in a ditch. And along the side it said Jodrell Bank Project Able. And it was splashed all over the Manchester Guardian, so it wasn't secret at all. And so it arrives there at Jodrell, and the Americans try and send a probe to the moon. And this is the team that came along. And these colour photographs come from William Young. And if you go on to Flickr, put in William Young Jodrell, you'll find these pictures. But being Americans, they had a nice fancy colour film, so we got some nice pictures. Now, I came across this, which is in 1959, they electrified the railway, which went right by Jodrell. And if you remember, that he went to Jodrell to avoid interference from the trams. And here we've got a railway next to it. Well, the thing is when I was there, it never troubled us, and I was told they'd done something to stop the interference, but I always thought, oh, there's a Faraday cage around it, or they freewheel through it. But I haven't been able to find anything that says whether they did anything at all, put in better suppression there, I don't know. But it's not the locomotive that intrigued me, it's this, which shows the telescope upside down. Because when they first built it, it was balanced. And remember the semicircular wheel, that's just to suppress the flutter. It doesn't support the weight. And initially they were going to have a tower which trundled out into the middle so they could change aerials. But they decided, oh, that wasn't going to work. And you think, well, this is crazy. Why didn't they just shin up the mast in the middle? But here we are. This is the Americans putting in their feed. So this is the dish upside down. And this is the aerial feed. And what intrigues me, there's only one chap with a helmet on. And this is it being winched up onto the top of the focus tower. Why on earth they thought this was easier than just going up the tower as they do these days, I have no idea. But you talk about health and safety. This is no helmet, is standing on the box. And these look like containers for liquefied air or something. And they're holding that up through this hole in the dish. And this is also what intrigues me, this very highly accurate dish. And they've cut out a square of it, which is all bent and misshapen. And you think, why did they do that? It's crazy. Now, what happened is that in later years, because this semicircular wheel didn't carry any weight, the trunnions and the cones that supported all of the weight of the dish started to have metal fatigue and cracks were appearing. So what they decided to do is to take a lot of the weight off it and put two semicircular girders which actually carried about a third of the weight. And these were supported on rollers. And then there was another railway track around the middle and some more bogies to take the weight off. And this is a picture I took in 1970 when they were doing the work. Now, if you look at the modern day telescope, you'll find there's an extra set of bracing girders because what happened is that in January 1976, 2nd of January, we had a storm like the one today. And it went directly over Jodrell with winds of over 90 miles an hour. And although the dish could take it, the problem is that when there were high winds, the telescope controller would point the towers of the telescope into the wind. And it was so strong, they bent. And these semicircular girders resting on the rollers, they were within a couple of centimetres of falling off. And if that had happened, the whole thing would have come down. So once that storm was over, they very quickly decided, oh, we better brace the towers. And so far, well, this storm today isn't going up there, so they're okay today. But the other thing they did is because this added weight to the back, it wasn't balanced. So what they did is put another dish on top of the existing one. And this is a shallower dish, and the central tower now pokes out. It's not in the plane of the dish at all, it sticks out. And then you've got a focus box, which is about 2 meters across. And you haven't got this crazy idea of inverting the telescope. There's a little lift. And when you go up this lift, you open the trapdoors by the focus box, and then climb up a ladder and then go in the focus box where you put all the receivers and the cooling and all that sort of stuff. So that's what it looks like now. But back to the Americans and their space flight attempts. All of their rockets failed, except for one, which was Pioneer 5. And the original intention was they were going to fly by Venus, but the launch was delayed, so Venus had moved out the way. So they just launched it into space between Venus and the Earth, and it's still going around there today. And this is part of the communications equipment they installed at Jodrell, so they could actually command it from Jodrell itself. And to do the necessary, they employed Princess Margaret, and here she is pressing the button. And I think she was led to believe that, oh, it was a dummy button, but it was the real button. And they sent this, they sent a signal to separate it, the probe from the rocket, and also to switch on a more powerful transmitter. So this is commanding the spacecraft. And at the same time, they were also tracking Soviet probes, because the Soviets launched one probe that crashed into the moon and another that flew by and took a picture of the backside of the moon. And I think this is amusing. There was a cartoon in Punch that said, "Jolly demoralising tracking other people's satellites and on something that isn't yet paid for." Because at the time, they were in debt. And Lovell kept getting phone calls from the media saying, "Oh, are you tracking this satellite, blah, blah, blah." And his phone rang, and it's like at the moment you get a nuisance call. You think, oh, it's another nuisance call. He picked it up, and it's Lord Nuffield saying, "Oh, you want 50,000 to pay off your debt?" So that was it. He paid off the debt, and then everything was fine afterwards. So a combination of the Americans paying money to use the telescope and the fact that it was in the news all the time, and they're on the people's best sides. But the trouble was, it was renamed the Nuffield Radio Astronomy Laboratories, and eventually, I think in the 90s, they gave up. I don't know if they fell out with them or what, but it's not called that any longer. And it was an everybody's good book, so much that he was knighted in 1961. This is wife and daughter. I don't know which one, but how am I doing for time?
25 to 9, so wind it up fairly.
Yeah, right, okay, I'll try and be quick.
Just to give some time for some...
Yeah. This is interesting. This is from Hansard. So it's a record of what happened in Parliament in 1962. And it's some MP asking the Secretary of State for Air, asking the number of days in each month when Jodrell was being employed as part of the early warning system. And there were two RAF officers constantly on watch at Jodrell, ready to leap to a radar if there was any danger of a missile being launched from Russia. And the reason why this is that they were building Fylingdales, which was the early warning station. But the problem was the workers kept going on strike. So it should have been finished in about 1960, but it wasn't finished till 1963. And in the meantime, Jodrell was there on standby, that if the worst came to the worst, they'd switch the radar on and say, "Oh, you got 5 minutes before you're all blown up." And these golf balls, they're not there any longer. They've got a much more sophisticated phased array radar now. This photograph's interesting because there's a chap in our society. He used to work for a photographic agency, and one day one of his colleagues flew over Jodrell and took this picture. And so this is the situation in 1964, and you can see it's looking far more professional now. You've got what was called the Mark I telescope, now the Lovell telescope. You've got the Mark II, which I'll talk briefly about in a minute. The 50-foot on top of this is the control building for the Mark I. That was always used to track space probes. Whenever the media showed Jodrell, they'd always show the Lovell dish. Well, that wasn't what was used, it was the 50-foot. That's since been replaced. It was damaged a few years back. 30-foot was the original sort of prototype for the Lovell dish, that little dish I showed. And the other interesting one is this Smith-Clark. It's a bit difficult to see. That's actually an optical observatory which was donated by Captain Smith-Clark from Coventry, who was involved with developing the iron lung. And he donated one of his telescopes to our society, but the other one he gave to Jodrell. But they never used it, so they donated it to Salford University, and it's still there if you want to look through it. So that's what it looked like in '64, and I'll briefly mention the Mark II. In 1960, Lovell wasn't satisfied with a 250-foot dish. He wanted to build this, and this is a sketch he gave to her husband. He said, double the height, 500 feet, and the width is from 1,500 to 15,000 feet. So he wanted to build this huge thing. And her husband said, oh, perhaps you better have a prototype. And this was the prototype. And it was built by Head Wrightson, and this is their advert from '63. And it's 38 by 25 metres, 12-metre focal length. And there's a picture of it being constructed in Thornbury-on-Tees in 1963. You can see this sort of lattice work design. And this is it on the floor of their workshop. And this is it being constructed at Jodrell. And what they did is they took away where the transit telescope was and plonked the Mark II in its place. So this is the Park Royal hut next to it. And it's made out of pre-stressed concrete. I don't know whether it's going to that foamy concrete, and uses concrete weights at the bottom. And that cost $239,000, so a bargain. And it was controlled by a Franti Argus 100. And each JK flip-flop cost £25 when it was made. It had 12K words, a 24-bit core store, and used germanium transistors. And this is the control panel of it. So you've got 24 switches to put in an order code to say read the tape, because it was all punch tape programmed. Later on it was moved to the Mark I, and they replaced it by an Argus 400. And the Argus 400 for the Mark II was used to move the telescope and also to take the results from it. And there was also another Argus 400 which was in the Mark I observing room, which solely just did the analysis. And I always remember my first program I wrote on it, it crashed it and all the lights lit up. There were about 100 lights on this. And then somebody said, oh, what about the operating system? I said, operating system, what's that? So I completely ignored the operating system, and it didn't like it and crashed my program. And the other telescope they made was the Mark III. And this was the same as the Mark II, but this had a wire mesh dish, and it was supposed to be transportable. So the idea was that you made an interferometer out of it. So you put it some distance from Jodrell, and then took some readings and then moved it like Jennison Dasgupta had done on the back of a lorry. So I don't know how big the lorry was for this. It was mounted at Wardle and it was never moved. And it was scrapped in '96. I crashed this once. I got students were allowed to drive the telescopes, the Mark II and the Mark III. The Mark I, you had a controller, a chap who sat there, and you weren't allowed to do anything. And to drive it, you had to pass the driving test. But the thing was, one day I was observing with it, and I got distracted by what other people were doing in the observing room, and didn't notice it was getting closer and closer to the horizon. And they had some safety valves which ditched the hydraulic fluid if it got.
I then lived in relative peace and still do so. And I retired from Jodrell in 1981, but I am privileged still to use an office there. And I'm delighted still to be able to go there whenever I want to and try to understand what the young people are now doing. I think I perhaps ought to end my story there.
I'll use this microphone. Oh, it's working.
Right. Okay. Thank you very much. It's fascinating how much went on, and you then see this enormous thing, but no idea of the background.
Well, that's right, because it all looks very organised and very planned and laid out, but it wasn't.
Yeah.
It was never meant to be a radio observatory, and it was never meant to be at Jodrell, and it all hinged on this crucial mistake.
Yeah. Well, later on about that, I've also had a little bit of problem I mentioned from time to time, discovering that Mr. Watt made mistakes in the early work on the steam engine downstairs. It does happen. Right. So, thank you very much indeed.
Thank you.
Have we any questions? Yes?
Whether I can answer them.
Sorry about my sloping off from time to time.
Watching the unfolding story, I can't help but think it started off on almost a Heath Robinson basis, and it got bigger and bigger and more equipment, and ended up, quite frankly, with frightening size of the dish. How was it all funded?
Oh, well, that was a problem. It wasn't. They had a grant, but that was for only the original estimate. And when they changed the design from a wire mesh to a solid metal mesh, and then added the extra girder on, that increased the cost. And also the price of steel went up. So I say it's a bit like HS2. They kept spending this money they didn't have. And eventually he put out a sort of crowdfunding request, and there were schoolboys sending in their pocket money to try and cover the cost of it. And he went back to, I don't know who gave the grants out to science at the time, but he went back to them and got a slightly greater grant, but said, we'll only give you that if the university contribute. And they weren't keen on contributing. And when they did eventually put some contribution in, it still wasn't enough to pay for it. So he relied on getting money off the Americans like that. And that's why there was still that enormous debt that Lord Nuffield paid off. But he almost went to, as I say, he almost went to prison. And the workers went on strike. And Husband himself, the consulting engineer, sued Lovell for £1 million. But he later retracted that, and they ended up, good friends. So, yeah, he was in dire straits.
Did the university have much?
Yes, following on from the matter of the finances, really, to what extent did the university have any control over all the work that was going on and so forth, if any?
Oh, well, they didn't. They didn't. That was the problem. Yeah, Lovell seemed to be his own master, really. I mean, they gave this initial amount of money, then really left him to it. Yeah, it was like originally, if you remember, he was only supposed to be there for 2 weeks. But Blackett was distracted by work on atomic energy and atomic weapons and things. And so I think people just sort of forgot about him. And they said, oh, have this money, we'll wait and see it when it's completed. And that was about it, I think.
Right. Is there anything else? Well, thank you very much. And
yeah, I hope you found it interesting.
yeah, the whole background is when you begin to realise all the things that have gone on behind the scenes that you don't hear about, and that often is a more interesting story because you realise how people who have battled through all sorts of problems. It's great. So thank you very much.
Yeah, that's it. Thank you.